All right, so this is chapter 12, Oscillatory Motion. So in this chapter, we're going to be learning about um, what we call oscillatory or periodic motion, and specifically specific type of oscillatory motion, which is called simple harmonic motion. All right, so oscillatory or periodic motion, as you can see, right, is the motion of an object that regularly repeats. That means an object that goes back and forth with respect to some kind of equilibrium position. And one good example could be, let's say you have a ball and there's a marble, and then if you let go of the marble would like to go and sit at the equilibrium, which is at the bottom, which we call, let's say, x equals 0. But if you move it to some position, let's say A from equilibrium, and let go of from that position, what it will do, it will go back toward the equilibrium, but since it would be speeding up all the way to the equilibrium, it's not going to stop. It's now going to go up some distance, and if there is basically, uh, let's say, if it's rolling or if it's sliding without friction, it will go to the same position A, but on the other side. So let's call this negative A because it's to the left, and it can just go back and forth with respect to this equilibrium position x equals 0. And this is an example of a periodic motion. The object returns to a given position after a fixed time interval. Eventually, we know that in real life, marble or whatever object, right, it is, it will just slide down and slowly come back and stop in equilibrium. But we can simplify our calculations and our problems um, by assuming that, so let's say there is no dumping, which means that there is no type of let's say effect where it will eventually slow down and stop. And if it's an object that going back and forth, let's say we can assume that there is no external forces that's going to slow it down, so it can in a way go back and forth for a very long time, or simplify, can say forever. All right, so now the periodic motion is, again, any type of motion that repeats itself, right? Basically repeats itself. So let's say the butterfly wings, right? Back and forth, repeating. Earth going around the sun. It's also a periodic motion because Earth takes 1 year to go back and forth, and then another 1 year, another 1 year. And the moon going around Earth, right? All of this type of any type of thing that basically, a periodic. You drop a ball, it goes, hits the ground, comes up, back and forth, right? That's also a periodic motion. Now, we will be considering very specific type of periodic motion, and this is known as a simple harmonic motion. Now, not every periodic motion a simple harmonic motion, but every simple harmonic motion is a periodic motion. That's why periodic motion is more general category, where simple harmonic motion is subcategory. But all the simple harmonic motions are periodic motions. Now, what's the difference? Well, the difference is in the way that force is acting on the system when the object is being displaced. So let's say when there's a displacement, we want to look at where the force acting on the object to restore it toward equilibrium, right, will always be in the opposite direction of the displacement. So that's very important thing. That means if a force is always directed toward the equilibrium position, so this is the thing, toward the equilibrium position, the motion is called simple harmonic motion. And that's the important thing. And one of the things we're going to see here is two very, a good examples of a simple harmonic motion is the spring system and a pendulum. So that's what two things we're going to be considering and be concentrating on in this chapter. We're going to cover, in great detail the spring system and kind of briefly the periodic motion, the pendulum system. All right, so let's look at the spring system. We already have covered some, let's say, scenarios with the spring. When you take the spring, you stretch or you compress. Remember, there's this restoring force, right? Which we call it a spring force. But this is technically an elastic force, right? Because it doesn't have to be a spring. Any type of object that has, elastic properties, if you displace it from equilibrium, it can go back toward its equilibrium, right? We pull toward equilibrium because of the property of the system itself. All right. So now what we're going to assume here in our systems, always going to be a spring, and we're going to have a mass attached to the spring. And it's not, basically the mass will be attached. That means as the spring is moving, the mass is also moving back and forth with that. We have a spring that has a spring constant K, and then the block that has mass M. And let's say one thing we know here is if the system is in equilibrium, that means the spring is neither stretched or compressed, there is no force, no spring force, sorry. There's obviously right now there's a normal force and there's a gravitational force, but obviously they're not affecting the motion at all. They cancel each other. So what I'm talking about is the spring restoring force. And the spring restoring force is always zero, right? When the system is in equilibrium. The question is why? Well, because it's a restoring force. And there's nothing to restore when the system is in equilibrium. That means we take equilibrium and say that x equals zero. That's a position horizontal, let's say x equals zero. And when the system is in equilibrium, the force is zero. Now, it's possible, let's say, that the system is moving back and forth with respect to to that equilibrium, but in any case, every time it's passing the equilibrium position, that instant of time when it's at x equals zero, the force goes to zero. That's one of the things we're going to see later on. All right, so let's take the block and stretch it, or pull it to the right, which basically makes us, spring stretch. And one of the things we'll see here is our displacement here is to the right, right? We are displacing the system to the right. Right away, there is a, restoring force, the spring force. So the position is positive, right? So position is positive, and the restoring force, in this case, is going to be negative. And the reason it's negative because it's pointing to the left, because that's where the equilibrium is. It is pointing always toward the equilibrium. And in this case, it happens to be pointing to the left because that's where the equilibrium is. Right. So that means if the displacement is to the right and the displacement is positive, force is to the left and force is negative. Remember, that was one of the conditions for the um, simple harmonic motion. Okay. But it has to go both ways. That means if I'm actually, instead of stretching, compressing the spring, so let's say displacement is to the left. Well, if the displacement is to the left, then force in this case should be in opposite direction for the motion to be simple harmonic motion, and it is. If the position is negative, right, then the force is, positive, which means it is pointing to the right. Again, why? Well, because that's where the equilibrium is. Force is always pointing toward equilibrium. That's why this is known as a restoring force. No matter where the object is moved, its goal, its purpose is to restore the system back to its equilibrium. All right, so one of the things that we can see from here is the motion of the block to the right or to the left, right, or the displacement positive or negative, always corresponds with the force being in always in opposite direction. Displacement is positive, force is negative. Displacement is negative, force is positive. And then one of the things we have here is this relationship is given with this equation where spring force equals negative kx, where this is known as a Hooke's law, right? So we mentioned that before. So this is known as a Hooke's law, where spring force equals negative kx, which means the spring force is not a constant force, it's a variable force, and is proportional to x, but it's also proportional to negative x. And that negative represents that difference in direction for the spring. Displacement positive, force negative, or displacement negative, force positive, right? Remember. So, and obviously the K is a, proportionality constant. K is a spring constant or proportionality constant, and it is always positive quantity. K is always positive quantity in some newtons per meters. All right. So one thing we can have here, this is a spring force, which also always equals to mass times acceleration of the system, right? Horizontal, because this is basically the motion will be always along the x-axis. Now that means if I divide both sides by m, then we basically get this equation where acceleration equals negative of, x, where k over m is more or less, our constant of the system, right? Spring constant and then the mass. That means more or less you can assume that if you have a block moving back and forth, the spring constant represents some information about the spring itself. Spring constant K is sometimes also known as a stiffness constant. So, the value of k, if it's like, let's say, in hundreds or thousands, that means it's a more or less a stiff constant, stiff spring. And if the constant is like, a few newtons per meters, maybe like, let's say, tens, right, something like that, then it's relatively loose. And obviously the m is the mass of the block. We usually assume that mass of the spring is too small compared to the mass of the block, so we can always ignore that. The m in this equation pretty much only in terms of the mass of the block. Okay. In actual experiment, we do take into account the mass of the spring. We usually say then, let's say the total mass is m plus mass of the block plus 1/3 of the mass of the spring. But you can see, right, already, we take any equation is 1/3 of the mass of the spring plus, the mass of the spring generally much smaller than, let's say, this mass of the block. So in a way we can always ignore. So if this is like, let's say, 10 kilogram, and this is like, let's say, I don't know, 1.1 kilogram or something like that, you can see, right, it's small enough that we can more or less ignore that. But important to understand that this equation is what makes a spring system more or less simple harmonic motion, because acceleration or force is proportional to the negative of displacement. You can see, right? Acceleration is proportional to the negative of the displacement, where k over m are constants. All right, so force described by Hooke's law is a net force in Newton's second law. So basically, just what we did, right? Negative kx equals m times ax. Divide both sides by mass, and we get that. One thing we're going to see in a little bit, that this, k over m is kind of like an important, ratio as well. So k over m is also defined as angular frequency squared. So this is known as angular frequency squared. So we can also write this as negative omega squared times x. Acceleration k over m is equals to omega, omega squared. Or you can say that if you square both sides, then omega is equal to the square root of k over m. We're going to be using this quite a lot. Anyways, acceleration is proportional to the displacement of the block, and the direction of acceleration is opposite the direction of the displacement of the, from equilibrium. And this is pretty much what makes the system a simple harmonic. So the object moves with simple harmonic motion whenever its acceleration is proportional to its position and is oppositely directed to the displacement of the equilibrium. So you can say either acceleration or force, right? Because force and acceleration, always proportional. So the net force, remember, equals mass times acceleration. In terms of vectors, a and f always in the same direction. All right. So since force is not a constant, that means it's not constant. It changes with not time, but with position. So it's force, right? That means, let's say when the block is moving back and forth, I cannot use kinematic equations to describe its motion, because remember, kinematic equations were for the constant force, constant acceleration. Okay, that means, for example, if you have the block, you stretch it to some position, x. So from equilibrium position to some position x, and you let go, how long it will take to get, let's say, somewhere over here, or let's say what will be the speed when it's right there, right? I wouldn't know. Or maybe like somewhere over here, I wouldn't know. I can't use the kinematic equation to describe that, because a is not constant. I can't use kinematic equations to describe that. So that's why one of the things we're going to see here, we need to come up with new equations, new way of describing this simple harmonic motion. And this is a type of motion that we haven't seen, before. We will be, deriving that more or less, right? So looking from the sort of like from experimental point of view and things like that, and be able to describe when the system oscillating with simple harmonic motion, what is the graph representing that? We know what are the equations or the graph representing uniform motion or non-uniform motion, but what is the graph or equation representing simple harmonic motion? All right. So one thing we can talk about here is this. Um, you know, if you take this, let's say the spring system from equilibrium. So let's say here's the spring from equilibrium. You take it and you stretch it to some position x. Here's position X. Now, assuming there is no friction, so friction is equals to 0, if I let go of the system, then the system going to be pulled to the left because of this restoring force F. As it's being pulled to the left, it's going to go and come back, but it will never go beyond this position X. That means this position X is going to be always its maximum positive displacement or maximum displacement to the right. So X max is equals to, then what we're going to say, we're going to call this an A. So X equals A, which means this is where the black going to be released from, and that's going to be maximum displacement the black going to have, which means then acceleration, which is negative k over m times x. This is going to be then for the maximum acceleration because this is x equals position A. So x equals A, and I can call this plus A, which means this is basically where the acceleration is going to be the maximum. But since there's a negative, in a way, it's going to be the maximum negative acceleration for our spring. All right. So we're always going to start, let's say object when it is in that position, right? Think like this. If you take it and pull it to the right to that x equals plus A, and when you let go, it's always going to start from rest. That means the speed is always going to be 0. Okay, so always, 0 when object is at that position x equals A. All right, so which means that whenever the object, right, whenever object start at maximum displacement, it's going to have a, maximum acceleration, positive or negative, depending if it's going to be to the right, into the right of the, or like let's say equilibrium position, or to the left of the equilibrium position. But acceleration going to be maximum. So let's say right now, let's consider x equals A. So you're going to have then maximum acceleration, but it's going to be negative. But then the speed at position A going to be 0 because you're always going to start from rest. And even if it goes to the left and comes back and reaches position A again, because remember it's oscillatory, right? Goes back and forth. It's always going to stop at x equals A before going back again. All right. Now, you have more or less, 3 extreme points. There's also equilibrium position. Think like this. If you let go of the black from x equals plus A, then the restoring force is going to pull it to the left. And it's going to be accelerating all the way toward, equilibrium position. Remember, acceleration is not constant, but it is still accelerating all the way to the, equilibrium position. That means the speed is increasing, increasing, increasing. But remember, closer you get, let's say closer the x gets to 0, then the force, positive or negative, doesn't matter, right? Force gets closer to 0. Means that acceleration gets closer to 0. Because remember Hooke's law, force is equals to negative kx. X is 0, force is 0. Well, force is 0. Well, the acceleration is 0 because of, the equation A equals negative k over m times x. If x is 0, A is 0, and F is 0. So that's why when the black passes through the equilibrium position, there is no acceleration. As soon as the object, right, the black, moves from equilibrium to the left, even an inch, then the force changes direction, which means then after that, object moving to the left with the negative direction force or acceleration going to start slowing down. Right? It's going to start slowing down until it eventually stops at x equals negative A position. But from positive A to 0, it's been speeding up. Then from 0 to negative 8, then slowing down, which means that the speed is always going to be the maximum when it going through that equilibrium position, because you speed up all the way to that position, then you start slowing down right after. So that's why, you can say then the velocity, right, or the speed is always the maximum at this position, okay, at the equilibrium position. Now, what we get here is then the black that basically going back and forth. So it's a continuous oscillating between negative A and A. So think like this. If this is the spring, you start from this position x equals plus A. Let's say this is equilibrium, and this is x equals negative a. So then the black gonna pretty much, if you let go, right, it's not gonna have any speed here. So then if it starts moving to the left, it's gonna reach this position with the maximum speed. But remember, if it has no speed at point A, it has a maximum acceleration, but it's gonna be negative. And the reason is because the restoring force is going to be toward the left. So the acceleration, that means negative force, negative acceleration. You reach equilibrium position, speed is the maximum, but the force is zero and acceleration is zero. Now, as soon as it moves to equilibrium to the left, the force is now changes direction. That means when the black reaches x equals negative a, the speed is zero, acceleration is maximum, force is maximum, and this is basically acceleration, right? Is positive. Why? Because acceleration is negative k over m times negative a, because x is negative a. They cancel each other, so it becomes k over m times a. So it's positive and maximum. That means same thing with force, positive and maximum. So here the force maximum and negative, acceleration maximum negative, speed is zero. You can see, right? Kind of like, a perfect symmetry. Speed is zero, acceleration and force maximum but negative. Here, speed is zero, acceleration, force maximum but positive. And then at equilibrium position, speed is maximum, but acceleration and force are zero. And that's kind of what we have. That means, those are the three extreme points: x equals plus minus a, and x equals zero. Those are the three extreme points, right? The maximum displacement to the right and to the left, and the equilibrium position. And those are the quantities for, let's say, let's say motion quantities, right? Force, acceleration, speed, and things like that at those three, extreme points. Now, remember that force is a conservative force, the spring force. That means in the absence of friction, this motion can continue forever. That means if you let go the spring from x equals plus a, it will go and always come back to x equals plus a again, because there is nothing to dissipate, energy, right? And nothing to slow it down other than, let's say, the spring force. But spring force basically acts such that it is speeding up and slowing down, speeding up and slowing down, exactly same, proportionality, right? And you get exactly same displacement, x equals plus a negative a, every time it goes back and forth. Obviously, real systems do have some friction, and that's what we call damped oscillation, which is at the end of this chapter. I won't be necessarily going over that, so we don't have to, cover that. Let's say we're only going to be considering a simple harmonic motion. A simple harmonic motion means that no friction. Okay, object going back and forth, where force is this, negative of the displacement, but there is no friction. All right. So now, one of the things we have here is in terms of looking at all of this from the calculus point of view. Again, this is just a relatively straightforward derivatives, which we already done before. Remember, so you take the position, then if you take the derivative of position with respect to time, remember that was velocity, then you take the derivative of velocity with respect to time, then that's acceleration. But since velocity is the derivative of position, that means if you take the derivative of position, like let's say, second time, which is basically what we call velocity, right? That means you can say that acceleration is then the second order derivative of the position. Okay, that's why acceleration, which is dv dt, it's also equals to d square x dt square, because acceleration is the second rate derivative, second order derivative of the position. Now the question is this: so if you have d square x dt square equals negative k over mx, which is basically equation that we already looked at before, a equals negative k over m times x. Now what we do from here, remember, is we then define the k over m to be omega square, right? Omega square, we just basically say that omega square equals k over m. And This omega is known as angular frequency. Angular frequency has units of radians per second. Radians per second. That means this equation becomes, acceleration, which is d square d square x over dt square equals negative omega square times x. Okay. In a way, this is equation for the simple harmonic motion mathematically. That means in a way, what we have is this: you take some kind of function of x, you take the derivative of that function twice, right? They take the derivative of two times or twice, and you get negative of the same function times some kind of constant. Okay. And the question is that what type of function do we get? What type of function satisfy these equations? That means, for example, if it's a power function, I don't know, let's say x equals, t squared. That means, will I get the x, take the derivative of that two times and get negative 2t squared? That's what this equation tells you. Well, if you take it one time, you get 2t. You take the derivative the second time, you get 2, which means that it doesn't satisfy. That means x is not a power function. That means, the graph is not a parabola or something like that. Because t squared is something like that, right? And taking the derivative two times, we didn't get the same thing, but negative of that times some constant, but we got just constant and nothing else. And that's one of the things we're going to see. What type of, graph or a function satisfy that? But before that, kind of look at, sort of like, let's say what we have. Think like this. So this is being plus a, and this is, let's say, being negative a. Those are the two positions, right? The two extreme position, and here being x equals 0. So you can see, right, the spring basically oscillates back and forth. Now you have three vectors: force, then displacement, actually four, right? Velocity and acceleration at the bottom. And look at how all of them are related to one another. So look at, let's say the top two, which is the spring force and then the displacement. See, every time when it's moving to the left, forces to the right, moving to the right, forces to the left. We can see, right? And the force is increasing with position change. More you stretch, greater the force. But it's always in opposite direction, but still, it's increasing with the, force. That's why with the displacement. So that's why force is equal to negative k times x. So it's proportional to x. Also look at velocity vector, which is 0 at x equals a. See, it's 0 here and 0 there. But it's maximum, right, when it's going through the equilibrium position. And then obviously the last one is acceleration, which follows the force. Look at everything is just basically exactly in terms of the force. Same direction, same type of change, because, acceleration also negative k over m times x. It is proportional to negative of x. All right, so since we have this, since we have the system basically speeding up, slowing down, stopping, speeding up, slowing down, stopping, but the force and acceleration are not constant, we cannot use any of those kinematic equations. So we have to understand what type of function can work with this. And then the function that technically satisfies this equation needed, as I mentioned, right, need a function x of, x of t, whose second derivative is the same as the original function with a negative sign and multiply by, omega square. Okay, that means we need this type of function. And one of the things we have here is this. So I can try to graph this by taking the spring system, let's say to x equals plus a. And let's say this is being equilibrium and this is being x equals negative a. And I'm going to try to graph this. So x as a function of time. Now, what I get here is this. At my t equals 0, seems like my position here is at a, so plus a. Then I'm going to let go. So think like this. Here I start at t equals 0, I start here. Then I let go. When I let go, this is, let's say, first segment. And during this first segment, what the block gonna do here is gonna speed up, right? Because there's a force to the left. So it's gonna speed up to the left, which means that I have to do a graph of an object speeding up, but to the left. And that graph, if you remember, looks like this, which is, object speeding up. Object speeding up to the right looks like that, but to the left, looks basically what I have over here in the graph. Then it goes from x equals 0, right? When it reaches x equals 0, it doesn't stop, remember, right? It starts moving to the left because it's been speeding up all that time. But as soon as it moves to the left, the force is now in opposite direction, which means that here's a segment 2 where it slows down. When it's slowing down, going from x equals 0 to x equals negative a. Well, slowing down, moving to the negative direction, is represented with this graph. This is slowing down, moving to the left. And it's going to go until it reaches 0, negative a. And when it reaches negative a is 0, that means my graph has to look like this with a negative slope, 0 slope, right? And then once it stops, this force, basically it's maximum, so that's pulling it to the right, back toward equilibrium. So then I have this segment 3, where now the black is moving from x equals negative a to x equals 0. But it's speeding up because it's, the force is pulling it to the right, and it's moving to the right, so speeding up, which remember, so this is the graph for speeding up to the right. As soon as it reaches equilibrium, again, force is basically now pointing in opposite direction. So segment 4, it starts slowing down. Now it starts slowing down, moving to the right, slowing down, and this is your graph. And what I have here is then this graph basically repeats itself, right? Because it starts going back and forth. And what I get here is basically a graph like this, which you can see, right, is nothing but a cosine function. Okay, so sinusoidal, right? Cosine function, because it starts from x, t equals 0, starts from a. That means my motion of the object going back and forth, speeding up, slowing down, all of those things is a sinusoidal, as you can see from here. Okay, you can basically plot it, and what you get here is a sine or cosine function, and that kind of satisfies, right? So think like this: if I'm saying my x as a function of time is equals to, let's say, a cosine function, right? Let's say, proportional to, for example, a cosine function. Now remember one thing. Let's say cosine of its argument, right? So cosine of its argument. Let me do it in terms of, like, let's say a t. Now here's what I have. If I take the derivative of the x with respect to time, which is the derivative of cosine with respect to time, remember what I get is negative sine of t. Hopefully you learned this in your calculus class. Well, what is the derivative of the sine with respect to time? Well, it's cosine, but I already had a negative. So then if I take the second time derivative of this guy, then I get negative of, derivative of sine is cosine, so cosine of t. You can see, right? I started with cosine t. I took the derivative 2 times. I came back with, well, cosine t again, but negative of that. And no constant, but because let's say I can put some constant inside the argument, then have some kind of constant. And that's what we're going to do. So our solution here is sinusoidal function. That means x of t is equals to a, which is the amplitude where we start, right? The maximum displacement. Remember, a is the amplitude, right? So amplitude, and it's always a positive quantity, always a positive quantity. That's why we say x equals plus minus a. That means, when x is negative, we should say negative a rather than we say a is negative. So it's a cosine. Now here I have omega t, which is basically an argument, making sure that, remember, so that means this is still a function of time. So even if it's a sinusoidal, this cosine has to change with time. But I can't have, let's say, cosine of t. I simplified in the previous example, because if I do cosine of t, means that my cosine has a second as an argument. That you can't have that, right? So argument inside the cosine function has to be in radians. So now that means what can I take and multiply the time with, so then the units are radians? Well, omega, right? Because omega, remember, is in radians per second. So if I do omega times time, become radians per second times seconds. Seconds cancel out, and I have radians. That's why we do omega times time inside the argument. Or remembering omega is equals to 2 pi times frequency, linear frequency, I can also replace it with 2 pi f times time. We can also do that. So we'll look into that in terms of this. So the linear frequency and angular frequency, they are related. All right, so then plus phi, where omega, a, omega, and phi are constants. They're constants of our motion, right? And then the cosine curve can be used to give physical significance to this constant. That means, for example, if it's a function of time, if you're going from, let's say, one, let's say plus A to another plus A, the time it takes for the system to complete one cycle. Remember the T is period, right? And that means, this is in terms of the period. How is period? Remember, period is the time it takes to complete one cycle. Period is also reciprocal of the, frequency is 1 over F. And, since, angular frequency and linear frequency are related to one another, I can also relate those two, right? So I can say that this is also a 2 pi over omega. So I can also do it in terms of, period is equals to 2 pi over omega by replacing, omega, frequency with omega, which is omega over 2 pi. So I get that equation. So we're going to see all of those things that are related to one another. But in any ways, this is my equation of motion. That means it's not a linear, it's not a circular, right? It is sinusoidal. That's why we call it simple harmonic motion. And simple harmonic motion of a system oscillating back and forth is, sinusoidal or cosine function, cosine or sine function. All right, so again, A is the amplitude of the motion. This is the maximum position of the particle in either the positive or negative directions. So that's why we can say that X is equals to plus minus A. So those are the extreme points, right? So those are the three extreme points. Omega is called the angular frequency, and omega is equals to square root of k over m. But we also saw that omega is equals to 2 pi times frequency, and since frequency technically is 1 over the period, it's also equals to 2 pi over the period. So we're going to see all of those relationships. So, but those are equations for constant in our in our problems. So angular frequency as a unit of radians per second. Phi is the phase constant or the initial phase angle, also in radians. And we can define a new analysis model as the particle in simple harmonic model. That means we talked about, particle model, we talked about, a rigid model, circular model, right? And this is now a particle in a simple harmonic motion model. Okay. All right. So a lot of times the amplitude and the phase angle, right, or phase constant are determined uniquely by the position and velocity of the particle at t equals 0. So one of the things we're going to see here, I'm gonna basically show you this in some examples, right? So whenever the particle starts from t equals 0, right? So think like this: if the particle is at x equals a at t equals 0, then phase constant phi is equals to 0. Okay. So and then the phase of the of the motion is the quantity omega t plus phi. Okay. X of t is the periodic, and its value is the same each time, where omega t increases by 2 pi radians. So that's why when I have this, omega is equals to 2 pi over t, this equation, right? So if I cross multiply, so you can see, right? So if I do omega t, where t is the period, right, is equals to 2 pi, because you complete that much angular displacement, right? 2 pi radians. Now I can quickly show you, for example, why this is true. So think like this: so I have this equation, x as a function of time equals a cosine then omega t plus phi. Now imagine that I take my system and pull it to some x equals plus a, and then I let go and start the timer exactly same time. That means at t equals 0, my position of x is plus a, right? Because that's where I start. I start from plus a and I start the timer. And this basically what you have for the left side of the equation. That means, you can say x when t equals 0 is equals to plus a. But that's also equals to, according to the general equation, a cosine omega t plus phi. But I'm saying that t equals 0, and if t equals 0, that means this term is 0, right? Because they replace t with 0, that means this term is 0. And what I end up with is this: a is equals to a cosine of phi, because this part of the argument goes to 0, but phi stays, so becomes cosine of omega t plus phi, becomes just cosine of phi. And a equals a cosine phi. I can cancel the a, then have 1 equals cosine phi, and then do inverse cosine, where inverse cosine of 1 gives me 0. That's why phi is 0 whenever you start from x equals plus a. All right, so then the period is the time interval required for the particle to go through a one full cycle of its motion, as I mentioned, right? So the values of x and v for the particle at a time t equal the values of x and v at t plus period. And period is equals 2 pi over omega, is in seconds, right? And it is, one of the important, let's say, variables in simple harmonic motion. Because if you have the period related to the frequency, linear frequency, because t is equals to 1 over f, it also equals to the angular frequency, which is 2 pi over omega, right? And remember, since technically then omega related to other quantities, right? Like, omega is equals to square root of k over m. You can see, right? You can, in a way, relate all of those. And that's kind of what we're doing. So look at in the next slide, right? I have inverse of the period is called frequency. The frequency represents the number of oscillations that a particle undergoes per unit time. So they think like this. Period is how long does it take for it to go back and forth one time. And frequency is how many times it goes back and forth in 1 second. In a way, kind of that represents reciprocal things. So f equals 1 over a period, and it also equals to omega over 2 pi. So units are 1 per second, but we define that to be hertz. Hertz is a unit for the frequency and linear frequency. Units for the angular frequency, again, is radians per second. So we combine all of those three things together. So if omega equals 2 pi f equals 2 pi over the period, since f equals 1 over the period. Well, also omega is equals to square root of k over m. So you can see, right, you have this variable, spring constant k, mass of the block, period, linear frequency, angular frequency. And this slide basically shows how all of those things can be related to one another. Okay, so that's why more variables you have, easier for you to work with, right? Because I give you any two, you can find then the rest of them, basically, pretty much. All right, so since period is 2 pi over omega, and omega is square root of k over m, then period becomes, which is the important equation, is 2 pi square root of, since it's 1 over omega, it becomes m over k. So that's one important equation because it tells you that how long does it take for the spring to go back and forth only depends on one variable. Remember, the k is a constant, technically, but m is the mass of the block. And the period only depends on mass of the block. See, none of these quantities depend on amplitude. You stretch it 5 centimeters, 10 centimeters, 15 centimeters, doesn't matter. The time to go back and forth is exactly the same as long as you have the same mass. So the only thing the period depends is on mass. Only changing mass can change the period of oscillation. All right, so those are, variables. That means, like let's say again, we have, spring constant K, mass in kilograms, period in seconds, frequency in hertz, omega in radians per second. Then putting all those three things together, with our, let's say equation of the position that we talked about for a simple harmonic motion, you can see that we have three equations of motion. These are equations of motion. One is for the position. X as a function of time equals a cosine omega t plus phi. Now, what is velocity? Well, velocity is the derivative of the position with respect to time. That means I take this a and I take the derivative. That means, a cosine omega t plus phi. First, a is a constant, right? So it becomes a. Then you take the derivative of the cosine omega t plus phi. So the derivative of cosine omega t plus phi becomes negative of the sine omega t plus phi. That's where those come from. And then because the argument also has a t, then you take the derivative of the argument. So then when you take the derivative of the argument, right? So the derivative of the omega t plus phi basically gives you omega, because phi is a constant and omega t give derivative becomes t, and that's this omega then becomes that. That's where negative omega a sine omega t plus phi comes from. That means you first taking the derivative of a cosine omega t plus phi, which gives you a negative a sine omega t plus phi, then take the derivative of the argument as well, and that omega comes from there. Then you take this velocity equation and take the derivative of that second time to get the equation 3, which is for the acceleration. That means you have the constant, which is omega times a, then take the derivative of the, so negative omega times a, then take the derivative of the sine omega t plus phi, which gives you cosine omega t plus phi, and then take the derivative of the argument, and we know that argument is again just omega. That means now you multiply another omega, so it becomes omega square times a. And the negative sign stays because sine of t is equals to cosine of t. There is no negative. But when you go cosine of t, the derivative of cosine of t becomes negative sine of t. Okay, so that's why both v and a have negative, but not the position. Now, one thing we can do here also, recognize one simple fact is this. See, a equals negative omega square, then a cosine omega t plus phi. What is a cosine omega t plus phi? Well, that guy there, right? Just x. That means it's equals to negative omega square times x. Didn't we just start with this? Remember, a is equals to negative, k over m times x. And then we said k over m is just omega square. You can see, right? But this is now both of them as a function of time because they change with time. But those are our three equations of motion. That means we have acceleration as a function of time, velocity as a function of time, and position, velocity, and acceleration. How about the force? Well, it's F equals ma, right? Well, a is a function of time. Since a changes with time, well, so is force. Okay. Also, we can do it in terms of negative kx, where x as a function of time. You're going to get pretty much the same thing. All right. So this means that velocity, acceleration, and position, they all change with time, and they're all sinusoidal functions. All right. So because the sine and cosine functions oscillate between plus minus a, we can find the maximum values of the velocity. All right. Remember, right? If you're looking at the cosine and sine functions, they oscillate between plus minus a, which in a way means that we can go back. If I come back to here, so think like this. This is my x function. So this is the cosine function for the position. And then the coefficient that I have in front of it is technically represents my maximum displacement. So I can say that x max is the coefficient in front of the sinusoidal function, which is basically a. Now let's look at the velocity. For velocity, this is my sinusoidal function, and then the coefficient in front of it is this then omega a. That means then v max is then omega times a. Same way, I can look back for the acceleration. I can say this is then my sinusoidal function, and this is the coefficient in front of that, which then represents a max, which is then omega squared times a. That's what we can see here. See, x max equals a, v max is equals to omega a max is omega squared times a, which then we can replace omega with square root of k over m. And since this is omega, becomes k over m. That means you can also do it in terms of this. And I already, more or less showed you this already, right? A max equals k over m times, a, because maximum acceleration occurs only when, let's say x equals at a. But in any case, so what we have here is the frequency and period depends only on the mass of the particle. Again, this is something that I showed you, right? Period is equals to 2 pi, the square root of m over k. You can see, right? It only depends on the mass. And if I use the frequency, which is reciprocal of this, again, frequency also depends only on the mass of the spring, of the black hole. They do not depend on the parameters of motion. And the frequency is larger for a stiffer spring with the larger values of k, and decreases with the increasing mass of the particle. Okay, because the frequency, if I'm looking at it in terms of those quantities, equals to 1 over 2 pi, which is in the previous slide, then square root of k over m. So you can see, right? You increase the stiffness, that means you increase k, frequency increases. You increase the mass, frequency decreases, because frequency directly proportional to the spring constant, inversely proportional to mass. All right. And if I'm doing the graphs, then the graphs will be, remember, equation one for the position was a cosine. That means I can look at it in terms of, this being position plus a, and it's a cosine function going like that. Velocity was a negative sign, and if this is being the plus a, this is negative sign. And acceleration was negative cosine. That means negative starting from negative a, so it's a negative cosine. So those are the graphs for position, velocity, and acceleration. And you can see, right, velocity is 90 degrees out of phase. The acceleration is 180-degree out of phase with displacement. All right, so in terms of those graphs. And amplitude here of the graph is the A. Amplitude here is V max, which is omega A. And amplitude here is A max, which is omega squared times A. Those are, again, quantities that are important to know because sometimes you might be given those information specifically. All right, so now what we can do here is, in terms of using the initial conditions, we can find the phase constant, for example. So remember, so let's say consider a block set in motion by pulling it from equilibrium by a distance a and releasing it from rest at t equals 0. That means when it's at x equals a plus a, right, you release and you start your timer. That means this is the initial position at t equals 0. Right? This is the initial position at t equals 0. Again, that's why I can say x at t equals 0 equals then a cosine omega t plus phi, which means this left side of the equation is basically a, because that's what a is, right? X. So this is x initial, and x initial is a. So then this is equal to an a cosine omega times 0 plus phi, because t is 0, right? So that means that's why this term goes to 0. So it becomes a is equals to a cosine of phi. What it does then, I can cancel the a from both sides, and I can end up with then 1 equals cosine of phi. And again, phi here is equals to inverse cosine of 1, which gives me 0. All right. And then the same thing I can do for the, let's say, velocity at t equals 0 equals negative omega times a, then sine omega times 0, so then plus phi. Since this is the timer when the tx equals plus a, that means, my initial velocity is 0, right? So this is my initial velocity. So I can say 0 is equals to negative omega a, sorry, then sine of phi, right? Sine of phi. That means 0 equals negative omega a sine of phi, right? So now one thing I know here is omega is not 0, a is not 0. That means this product, omega a sine of phi, cannot be 0 because of omega or a are 0. It can only be if the sine of phi is 0. And under which conditions sine of phi is 0? Again, if phi is equals to 0, because sine of 0 is 0. And that's what we have, right? So using these initial conditions, x of 0 equals a and v of 0 equals 0, this means then phi equals 0, like I showed you. And the acceleration reaches extreme plus minus omega square a. Velocity reaches extreme at plus minus omega a. Okay, that means, I can look at it and do this graph, and you can see, right, if I start from plus a, then my graphs look like this, right? Where the time to go from plus a to another a is t. When it goes from plus a to negative a is basically half of the t, right? Period t, right? And then the same thing with velocity, right? When does velocity reaches, let's say extreme, right? Velocity reaches its extremes of, plus minus omega a. That means, and same thing with the acceleration. Okay, because remember, so velocity and acceleration, right, can be both positive and negative even when they're in terms of their maximums. Another thing we can do is this. So consider that you pull it, or you basically stretch it or compress it, right? Doesn't matter, right? Let's say you move it from equilibrium. So this says consider an oscillating block spring system, and then we define t equals 0 as the instant the block passes through an unstretched position of the spring while moving to the right. Thing like this. So let's say you move it to equilibrium, so from equilibrium to x equals negative a, or even it could be like, let's say you move it here, x equals plus a, and then you let go. But you wait until it reaches negative a, and then you're coming back on its way. When it reaches equilibrium, then you start your timer. That means you start a timer when it's moving from equilibrium, moving to the right, okay, at that position. That means this is the position of your block at when you start your timer. And it is moving with some initial velocity to the right. Okay. Again, you can basically do this, right? You can compress it to x equals negative a and let go, but not start the timer, but start the timer only after it reaches equilibrium on its way to the right. That means what I have here is this: x at t equals 0 is equals to, I have this equation, a cosine omega t plus phi, but x initial, which is this, right? X initial, because it's x equals t equals 0, so I can say x initial is 0, and is equals to a cosine omega times 0 plus phi, which means 0 is equals to a cosine of phi. Now, again, I can, even if you want, I can divide both sides by a, right? Which gives me 0 is equals to cosine of phi, which means then phi, if I do inverse of cosine of 0, this gives me pi over 2. Okay, this gives me pi over 2. Now, the same thing I can then do for the velocity. At t equals 0 equals then, or, the general equation is v as a function of time equals then a in negative omega a sine of omega t plus phi. We can get rid of those like this, right? And now I'm saying, okay, so this is v when t equals 0, which is equals to negative omega a sine of omega times 0 plus phi. And this is my initial velocity, and I have it's just v initial, right? Positive. And this is equal to then negative omega a then sine of phi, right? Omega a and sine of phi. And then what I get from here is pretty much allows me to find what a is, right? So in this case, I can use it to find a, because what I have here is this. So phi from this equation on the, in terms of position, I get is plus minus pi over 2, because plus pi over 2 or minus pi over 2, gives me the same, 0 for the cosine, right? Cosine, pi over 2 or cosine of negative pi over 2 gives me 0. From this equation, you can say, then what I get here is I get then a is equals to plus minus v initial over omega. So basically I get that, if I, get into like what the acceleration is. Okay, sorry, amplitude, not acceleration, what the amplitude is. Okay. Right, and this is by taking this from my position equation, and if I plug in over there, and I can see how those initial velocity, angular frequency, and amplitude are related to one another. Okay, because sine of pi over 2 gives you 1, then omega, then you can say, right, vi equals negative omega a times 1, or you get let's say vi is equals to negative omega a times negative 1 if pi is negative 2. So that's why you get plus minus, and you get that relationship. All right, so that means you get this, and sorry, my bad. So actually, when pi over 2 is positive, you get negative. When pi over 2 is negative, you get positive. So you kind of get that. That means from this condition, you get this. Phi is equals to plus minus pi over 2. And then a is equals to minus plus VI over omega, something like that. And this can then, combining those two together, what we get here is this relationship, right? So that means you start with that, x of 0 equals 0, v of 0 equals v initial, combine them together, and we get phi equals plus minus pi over 2. Okay. And from here, we get then, again, a is equal to minus plus vi over omega. And because of this, then because the initial velocity and amplitudes are positive, so this ends up being, phi as negative pi over 2. So, and where this is basically, your amplitude. So amplitude is, vi over omega. Okay. That means if you take amplitude to be vi over omega, this corresponds to negative pi over 2. And you put that negative pi over 2 over there. And that's your basically graph. That means, one thing you do here is you don't start your timer when it's at x equals negative a, but you start your timer when it reaches the equilibrium position. So then your x is basically actually becomes a positive sine graph, and then your velocity basically becomes positive cosine, right? If you kind of plug in everything in terms of that. That means if you plug in negative, omega t plus minus pi over 2, you end up with a graph like that. All right, so let's look at an example here. A couple of examples where we can then put everything together finally in some, let's say, a lot of equations, right? So you have 3 equations of motion plus Hooke's law and plus, equations that relate all of those different type of, constants. All right, so let's look at a cone. The cone of a loudspeaker oscillates in simple harmonic motion at the frequency of 262 hertz, which is middle C, if you're a music person. The amplitude at the center of the cone is A equals 1.5 times 10 to the negative 4 meters. And at t equals 0, x equals A. Now, that's an important information because as we learned, right, if x equals A at t equals 0, it means that phase constant here is 0. Now, what equation describes the motion of the center of the cone? Okay, that means what we need to do here is we need to find equation to represent the motion of the center of the cone, and we can do that by saying, okay, so it's x as a function of time is a cosine omega t plus phi, but because of the initial condition we can set phi to 0, so it becomes a cosine omega t. Now I know what a is, which is 1.5 times 10 to the negative 4 meters. Then I have cosine, and now I have omega. Now, how do I find omega? Well, remember, this 262 hertz is nothing but the linear frequency. So in a way, I can use that to find omega, which is 2 pi times 262 hertz. So this should be 1,650 rad per second. So it's 1,650, times t, like let's say. So that's my x as a function of time. All right, so part B says, what are the velocity and acceleration as a function of time? Well, which means that I have to take that and take the derivative, right? So basically then v as a function of time is negative omega times a sine of omega t, because again, phi is equals to 0. So then it becomes negative omega, which is 1650 times 1.5 times 10 to the negative 4 meters, then times sine of 1650 times t. Okay. And I combine them, and I'm going to get those omega times a together, which basically those two together is V max, remember, right? So becomes 0.25 meters per second, then times sine of 1650 times t. Well, acceleration as a function of time is the same way, right? So basically it becomes negative omega squared times a cosine omega t. So in a way, then what I do is, I do negative 16 1650 squared, then times 1.5 times 10 to the negative 4, then cosine of 1650t. So then acceleration, will be equals to negative 408 meters per second, then cosine of 1650 times t. All right, so then the acceleration and velocity is a function of time. Because if I have those equations, then for example, something like this, right? What is the position of the cone at t equals 1 millisecond? Then all I have to do is just take equation 1 and then replace the t with a given time. So I can say x when time is equals to 10 to the negative 3 seconds, basically, is equals to, 1.5 times 10 to the negative 4 meters, then times cosine of 1650, then times 10 to the negative 3 seconds. And I calculate, and I'm going to get negative 1.2 times 10 to the negative 5 meters. That means that is the position of the cone at, 1 millisecond. 1 times 10 to the negative 3, or just 10 to the negative 3. All right. Let's look at another example here. The position of a particle is given by x equals 7 centimeters cosine 6 pi times t, where t is in seconds. What are frequency, period, amplitude of the particle motion, and the first time after t equals 0 that the particle is at its equilibrium position? In what direction it is moving at this time? All right, so then what you do is this. So you say, okay, so x equals 7 centimeters, then cosine of 6 pi t. And basically compare it to the general equation where you have a cosine omega t plus phi. Right, so if I'm comparing directly, I can see that means my a is equals to 7 centimeters, and my, phi, my phi here is 0, and my omega is the coefficient in front of t, which is then 6 pi. Okay, so those are directly reading uh, from the function that we were given by comparing to the general equation. Then if I go and look at, part A, which is the frequency, well, one way I can find the frequency, remember, is by saying that it's equals to omega over 2 pi. Well, which is then 6 pi is the omega divided by 2 pi, right? So then we can see that this is just, 3, and pi cancels, so you get 3. Remember, units are, per second, right? So basically you can say that just hertz, 3 hertz. That's the, part A. How about part B? What is the period? Well, period is, number of ways you can find. One is you can say this is just basically 2 pi over omega, right? So 2 pi over omega, or we can say just it's 1 over f, right? That means it's 1 over 3 hertz, which is the easiest one. That means it's 0.33 seconds. All right. The C, which is the amplitude, but we get the amplitude directly from, the function itself, right? So you can say A is equals to basically 7 centimeters. There you go. Now, the, part D. So this was the easy part, right? So to get some of those, information. Part D, it says, what is the first time after t equals 0 that the particle is at the equilibrium position? In what direction it is moving at this time? Now, one thing we have here is this. We know that the particle has phi equals 0. Remember, phi equals 0 means that it started from position x equals, x equals a. Sorry. So x equals a, which means then we need to kind of get some information from that. At least that one information directly we get from that. All right, so for D, basically, because it's asking how long does it take for it to get to equilibrium position first time, then we can assume this. All right, so then x, as a function of time, equals A cosine omega t. I remember phi was zero already. So then when it reaches equilibrium, what is its position? This position is zero. It equals to A cosine omega t. Well, if I divide both sides by A, I can just cancel that A, which means it's zero is equals to cosine omega t. All right, that means cosine omega t. Now, what means that, let's say what I have here is, when is cosine of some argument equals zero? Well, clearly when omega t, if omega t equals pi over 2, right, then it is zero. Then if I, replace omega t with the pi over 2, it is basically zero. Now, which means then t is equals to pi over 2 omega. So I just plug in, right? Pi over 2 times 6 pi, do this calculation, and we're going to get 0.0833 seconds. That means it takes 0.0833 seconds for it to reach equilibrium position first time. Okay. We also now want to know in what direction it is moving at that time. All right, so it's a good question. So let's talk about that. So what we do for that, we take the velocity equation with respect to time. Right, so velocity as a function of time, remember, is basically derivative, right, of position as a function of time. Okay, that means we take the derivative of this function, so it's going to be then negative omega a sine of omega t. Right? So means negative, well, omega is 6 pi. So 6 pi times 7, well, it's 42 pi, right? Then centimeters per second as a units. And then we have then sine of, again, still 6 pi. This is my, equation for the velocity as a function of time. But then what I do here is, remember, it's 6 pi times time. I just replace time with, 0.0833. That means, replace that, plug in the time over there. So if I plug in the time over there, think like this. This whole thing is going to be positive, but then this is negative. So that means I get a negative over there. So that means if I do that, I'm going to get a negative number. By the way, don't forget, it has to be in radians, right? When you're doing this type of calculations, and not in degrees. But in any case, the idea here is we don't want to know the speed. We just want to know the direction. And one thing I know here is if I'm plugging over there, I'm going to get a negative number. And negative number means that at t equals 0, it is, velocity is negative, means it's moving in a negative direction. That means it's moving basically to the left at this time. All right, so let's look at the next example. So this is the example that I promised, right? So in terms of finding the phase constants for different, let's say, positions. So it says, what is the phase constant phi in equation x equals a cosine omega t plus phi if the position of oscillating particle at time t equals 0 is, 0, negative a, or some half a, thing like that, where a, remember, is the amplitude. That means we want to know what are those, values of the let's say phase constant phi, right? If your timer starts not at, at different positions, like. So let's look at, the first one, which is at you're saying x when t equals 0 is equals to 0. Okay. In a way, we already looked at this one, but let's look at here. So this basically, this is, remember, then this is equals to then a cosine omega times 0 plus phi, because t equals 0, then becomes a cosine phi. That means 0 is equals to, or a cosine omega phi equals 0. And obviously from here, I can get rid of a because, dividing both sides by a. And then from here, I can see then, phi is nothing but inverse cosine of 0. And that means that phi here is pi over 2, 3 pi over 2, right? And so on and so forth. Or, like let's say plus minus, and so on and so forth. That's for part A. Um, that means every time the object is in equilibrium, the phase constant can be like plus, pi over 2, plus minus pi over 2, or 3 pi over 2. And that depends, how many cycles, it's doing, right? So let's say if it's going back and forth, right, in terms of how do we know if it's pi over 2 or 3 pi over 2, right? So, there are ways, more or less, that we can find out. All right, so then the next here is this. So x at t equals 0 is equals to negative a. And this is then equals to then a cosine omega times 0 plus phi, which means that negative a is equals to a cosine of phi. Divide both sides by a. What we get then, negative 1 is equals to cosine of phi. And I can say, all right, then phi is equals to inverse cosine of 1, sorry, negative 1, which then end up being equals to pi. Okay, that means this is then what I get. If you compress the spring and let go of the spring, and let's say start the timer at that instant, then your phase constant is pi. Or if you stretch it to, let's say x equals plus a and let go, but only start the timer when it reaches the negative a, again, phase constant is pi. It means you kind of have to, use that phase constant, because phase constant in a way tells you where's your initial position, right? Um, when you start your timer, pretty much. Right, so C, it's x when t is equals to a, and is equals to a cosine omega times 0 plus phi, then is equals to then a cosine of phi, which means, this is a equals a cosine of phi, where you can, cancel the a's, right, which is 1 equals cosine of phi, which then we've seen already, right, means, phi equals 0. So phi equals 0 every time your starting position, right, is x equals plus a. And finally, a d, part D, when it says, when your x, when t equals 0, is equals to, a over 2. And this is equal to then a cosine omega times 0 plus phi, right? So then from here we can say then that means a over 2 is equals to, like this, is equals to a cosine of phi. Again, from here I can cancel the a's. That means what I have is this 1/2 is equals to cosine of phi. Phi is equals to inverse cosine of 1/2. And then from here calculate, and I can see it's equals to pi over 3, or plus minus pi over 3, right? That means every time the object, you start your timer when it's at x equals, a over 2, then the phase constant is pi over 2, and then plus or minus depending on in which direction it is moving, right? So remember that equation, right? You have to look at it in terms of, um, like let's say initial conditions for the velocity and position to determine that particular content. All right. So the next, what we have here is solving some of the simple harmonic motion problems instead of using those equations of motion, which are technically deals with vectors and time-dependent vectors and things like that. We can try to use all of that, calculation, right? Try to find those, solutions using the energy method, which we learned that sometimes is easier because, let's say in the spring system, the work is done by the conservative force and energy is conserved. That means mechanical energy is conserved in all of those simple harmonic motions involving, the spring. Now, what I have here is this. So you can see, right, I have the kinetic energy. which is 1 half m times v squared. Well, this is 1 half times m times, well, what is v? Well, v changes with time, and this is equals to negative omega a sine omega t plus phi, right? That means I take v and plug in over there and becomes, you know, this quantity there, which is omega square, a square, sine square. Everything is squared because you're squaring the velocity or the speed. That means that's my kinetic energy. And it also changes with position, right? Because every position you're moving at a different speed, that means the kinetic energy changes. Well, same thing with the elastic potential energy, which is 1 half kx squared. And according to equation, x as a function of time equals, a cosine omega t plus phi, right? That also changes with time. That means, taking and plugging over there, so we get this equation. All right. Now, what do we do? Well, again, because it's a conservation of mechanical energy, E is equals to then K plus U. Okay, that means it's 1 half mv squared plus 1 half kx squared. And then what we do here is this. I can rearrange that to, show that, remember, V is equals to, all right, so V is equals to omega A. And see, here I have V squared, which becomes omega squared times A squared. Remember, omega squared is K over M times A squared. That means if I take V squared and replace it with K over M A squared, then this becomes 1 half M times, K over M A squared, then plus 1 half K A squared. You can see, right, M's cancel out, and you have this basically 2 1 half Ka squared. And what we get from here is, because then if you adding those two together, right, obviously this one comes with the, sorry, this one comes then sine omega t, sine square omega t plus phi. Here I have then cosine omega t plus phi. But one thing we know from the identity is that cosine squared theta plus sine squared theta is equals to 1. So if I'm replacing v with that and then combining them together, adding them together, I end up with this in the parenthesis, sine squared omega t plus phi plus cosine squared omega t plus phi, and that's equals to 1. That means total energy then is equals to 1 half Ka squared. That means this is the total energy of the system, which is given in terms of 1 half Ka squared. All right, so same way we can then, again, we can, as I showed, right? So K plus U, which is, 1 half mv squared plus 1 half Kx squared. That means this is equal to 1 half Ka squared. That means, in a way, what we have is 3 different ways of finding total energy. Here's the total energy. Is equals to 1 half Ka squared, which is generally when, the object here is position x equals plus minus a, and it's purely potential. All is equals to 1 half mv max square, which means that object is at equilibrium, the black is at equilibrium, and x is 0, it's in equilibrium, so it's moving at the highest speed. So all the energy down is converted into kinetic energy. So let's say you have purely kinetic energy. Again, so let's say if the system is at x equals plus a, and this is the equilibrium, then all the energy is, kinetic, potential, because remember, it's kinetic plus potential. Since it starts from rest, all energy is potential. And that means total energy is 1 half Ka squared. When it reaches the equilibrium position, we decrease the potential energy all the way to 0, which means we increase kinetic energy all the way to the same value. So then the total energy is 1 half mv max squared. But whenever it is somewhere in between, then there's some kinetic energy and some potential energy. So it becomes 1 half mv squared, not the maximum speed, plus 1 half kx squared, not the x equals plus minus a. And then you have that. That means there's one way to represent total energy. There's another way. And then the third way is 1 half mv max squared. So they're all equivalent to one another, all representing the maximum energy or total energy. And because there's a conservation of energy, then your energy will always just go oscillate back and forth between your kinetic and potential energies. So it's either purely kinetic or purely potential or combination of kinetic and potential. And because of that, there is no energy dissipation. So all you can do here is this. Let's say give me position, I can tell you how fast it's moving, or tell me how fast it's moving, and I can tell you where it is. All right, so then what we can do from here is basically go to a diagram like this, or you can just see the charts. So think like this. So this is, let's say, starting from x equals plus a. You have maximum acceleration, negative maximum acceleration, but at that position, your energy, which is this is total energy, is purely potential. Is right. The orange is potential energy. Okay, so it's purely potential energy. So and this chart pretty much gives you everything. So x equals a, speed is 0, acceleration negative omega square a because it's maximum acceleration, no kinetic energy, and potential energy is maximum. Then when it goes and reaches the equilibrium, all then potential energy converted to kinetic energy. So then position is 0, speed is the maximum, acceleration is 0, kinetic energy is equal to the potential energy, right? Because all the potential energy is converted to kinetic energy. And the time it takes is quarter of the period. When it goes to the negative a, then again, all the kinetic energy now converted to potential energy. Position negative a, speed is 0, acceleration is maximum positive, no kinetic energy, and potential energy is maximum, and back and forth, right? So you can say it kind of oscillates like this, back and forth, and you have conservation of mechanical energy from potential to kinetic, then potential to kinetic, and or somewhere between if you're not any of those extreme points. So that's kind of, this chart will help you to see those extreme points and those things. All right, so let's look at then an example again. So one of the things about this energy approach, right, energy method, it allows you to then get the position or speed, right, but not necessarily a time related quantity. Let's say, for example, tell me position, I'll tell you how fast you're moving, or tell me how fast you're moving, I can tell you position. Because you could see, right, in those energy equations, there were no time. So it just basically speed and, which is kinetic energy, or the position from the potential energy, right? So that's, let's say some of the, I guess, limitations of this energy approach, but then we can combine everything together, right? Once you have the speed, then you can use that in a, equation of motion for the speed or velocity, then find when exactly, right, are you moving at that speed. That's another thing you can do. All right, so let's look at this example. So using conservation of energy, so we're going to find we're going to take a 500-gram block and a spring that is pulled a distance 20 centimeters and released. The subsequent oscillations are measured to a period of 0.8 seconds. At what position or positions is the block's speed 1 meter per second? And what is the spring constant? Right, as I mentioned, right? So you can see it is asking us to find position given speed. Or it could have asked you, okay, so for this position, let's say if it give you position, you can find how fast it's moving. In this case, it's giving you speed and finding, okay, which position or positions it is moving at that speed. All right, so some information that we're given. Okay, sorry. Okay, so we are given, okay, mass, and we are given an amplitude, right? 0.2 meters, and then the speed, 1 meters per second. Also the period, which is 0.8 seconds. Now, here's one thing I have. It's asking 1 meter per second. The easiest thing is to do this, to verify if this is the maximum speed or not. Because think like this, if it's maximum speed, I know which position it is. It's the equilibrium position. So maybe one thing we can do here is maybe we can find the maximum speed. But remember, maximum speed is equals to what? It's equals to omega times A. I have A, but I don't have omega. But here's the thing. It's asking you to find, let's say, the speed position, the speed position of a speed. But again, as I said, right? So easiest thing to find the maximum speed and see if it's maximum speed or not. All right, so we don't have omega, but we have the period. Remember, omega is 2 pi over the period. So in a way, I can find that, right? It's 2 pi over point 0.8. And I can use that to find what's my, omega. All right, so 2 pi divided by point 0.8. So omega equals 7.9 radians per second. Now then V max is equals to 7.9, then times 0.2. And I can calculate this to be 1.6 meters per second. All right, that means clearly this is not the maximum speed. So position is not x equals 0. All right, so we tried, didn't work. That means we have to go and try to find that position. All right, so the easiest thing to do is to find this using the energy approach. Again, we can find using the kinematics and all those let's say not kinematics, right, but the equation of motion that we derived. But you can see, right, I can do the same thing using the energy approach, because one of the things I have is this: if I have the maximum energy, amplitude, I can calculate maximum energy, which is 1/2 ka square. And since this speed is some position x, I know that at that position x, there's also going to be both kinetic and potential energies. That means the total energy over there will be in terms of some kind of 1/2 mv, x square plus 1/2 k x square. But their sum should also be equal to total, kinetic energy, which is 1/2 ka square. And I can calculate that, right? Because I have, amplitude. But, now one thing we don't have here is we don't have the spring constant k, right? We don't have spring constant k. And there are two things we can do, right? So we can actually, solve this problem without, let's say using the spring constant, or I can, use this, find the spring constant and then come back and use this. In the slides, I have the approach where I find the position without finding the spring constant. And here I'm going to show you how to, let's say, simply find the spring constant and then use that here. In a way, the same thing, but two different ways. Because what I can do here, I can use this equation, because remember, what I need here is, what I need to find is this position x, okay, just directly from this equation. But I need spring constant k, and I can find spring constant k because I know that omega is equals to, right, or omega square equals k over m, okay, and I already have the k, I already have the mass, and I have the omega, so I can basically find it from there. So I can say then the k is equals to m times omega square. So it's equals to 0.5 times 7.9 squared. And if I do that, I'm going to get k to be roughly 31 newtons per meters. Okay, now I have that. I can come back and I can cancel 1/2 everywhere. Then what I have is this: ka squared equals to mvx squared plus kx squared. Remember, my goal is to find x. So then becomes kx squared is equals to, ka squared then minus mvx squared. That means, I switch the side and move the mvx squared to the right. Divide both sides by k. Oops. And then I have my x squared. And obviously from here, just take a square root of both sides. Then x is equals to square root of ka squared over k just becomes a squared, then minus, what I have here is m over k Vx square. All right, so basically I have that. So it equals to then zero point 0.2 square minus zero point 0.5 over, k, which, let's say k is again 31, and times, 1 meter per second square. And if I do that, x, because this is square root, x plus minus, right? I'm going to get plus minus 0.15 meters, which means that this is being in equilibrium. Let's say this is being the amplitude 0.2, at 1.5, at 0.15, at both of those positions, the black will be moving at 1 meter per second. To the right or to the left, here to the right or to the left, doesn't matter. That means every time it reaches that position on each other side of the equilibrium, it is moving at that speed. Now, in the process, we calculated also part B. So this is spring constant K, and then this is the position. As you can see, right, we can basically go do this method, or just, another method that I have in the slide, where you can see finding X first by doing some rearrangements, or finding the, spring constant K, afterwards. But, both can, work. All right, so then the last thing we have in this chapter is the pendulum. As I mentioned, we are going to be considering simple pendulum. I'm not going to consider physical pendulum, and damped oscillation. So we're only going to be looking at the simple harmonic motion and the simple pendulum. And the simple pendulum also is the system that um, exhibits periodic motion. And the question is that we're going to try to verify if it also exhibits simple harmonic motion. And remember, the important thing about simple harmonic motion was that the system has a force that always going to be in opposite direction of, displacement. Okay. And that's what we can do. So imagine that you have a pendulum which is hanging vertically, and you have a string mass, very negligible mass of string, right? And you have what we call pendulum bob, which has a mass m. When it's hanging vertically, that's our equilibrium position. So let's say, here's, L and M, two variables, right? Length of the string and mass of the, pendulum bob. So when it's hanging vertically like this, we can take this to be equilibrium position. So X equals 0. And if you move it to the right or to the left, because it's attached to the ceiling, it will move basically some distance here, right? Some height h, and also some distance, some angle theta, right, to the right or to the left. As you let go, it then can oscillate back and forth. Okay. So here's then, let's say, if you're looking at as you move it to the right, so object then will be under two forces, tension and gravity. But the tension is always going to be perpendicular to, let's say, displacement. So in a way, because it's perpendicular, right, it becomes a centripetal force. Remember, and we learned that centripetal force doesn't do any work. That means, in a way, the one force that's responsible for it to go back and forth is the, a gravitational force. And the component of the gravitational force, see, let's say if you move it to the left, say the gravitational component is to the left. Sorry, you move this pendulum to the right, then the component of gravity will be to the left. And if you move this to the left, right, that means the displacement is to the left, then the force of gravity component will be to the right. That means the direction of the force, again, is in a negative direction of the displacement. So the tangential, force is mass times tangential acceleration, and force is negative mg sine theta, and acceleration is d square s dt square, where s is the arc length, right? And you can see, right, again, what you have here, there's a negative, as a indication that force displacement are in opposite directions. So you can reduce this using the what we call small angle approximation, where sine of theta is approximately theta. If theta, let's say, under 5 degrees, so sine of theta approximately theta. So then, you can replace that with that. And also, one of the things we have, remember, s, which is the arc length, equals, r times, and r times theta. In this case, r is L, so L times theta. So we can replace that more or less into, this derivative in terms of the derivative of theta, and then move the L to the other side. So negative G times, G over L, right? So this was like, let's say L times that, and divide both sides by L. And then here what we do, this simple, approximation where sine of theta is approximately theta. Okay. Again, so we started with negative mg sine of theta is equals to um, this square s, sorry, this square s dt square, and this becomes L times d squared theta dt, right? So and then if we divide this, um, we will then get, you know, divide both sides by L, right? Then I have d squared theta dt squared equals negative G over L. Okay. Negative G over L, because there was also M over there that cancels one another. And dividing both sides by L gives me this. This is the second order derivative of the angular position equals negative G over L times angular position, which means kind of similar thing. You take some theta as a function of t, you take the derivative of that twice, and you get negative of that theta times some constant. Okay, this means taking the derivative of that twice, you get some kind of negative of that function and some constant. And remember that constant before it was d square x dt square was equals to negative omega square times x. That means anything in front, the coefficient in front of x was omega square, and here coefficient in front of theta is G over L, and it is indeed also, omega square. So for the spring, omega square was K over M for the spring, and for the pendulum, omega square is equals to then G over L, or omega equals G over L. That means this is then angular frequency for the pendulum. Angular frequency of the pendulum. So angular frequency for the spring, omega square, or you can say omega is equals to square root of K over M. This is for the spring. And then omega equals square root of G over L for the pendulum. Because using this, we can look at the period equation for the pendulum. Remember, period for the spring was 2 pi square root of M over K. And for the pendulum, because omega is square root of G over L, pendulum equals to the 2 pi times square root of L over G, which means this. To change the pendulum period, you can only do that by changing the length of the string. It's independent of the mass of the pendulum. That means the pendulum bob can be 5 kilograms, can be 100 kilograms, it doesn't matter. What changes the period or frequency for that matter, right, is the length. So period and frequency of a simple pendulum depend only on the length of the string and the acceleration due to gravity. The period is independent of the mass. All simple pendula that are of equal length and are at the same location oscillate with the same period. All right. And in a way, technically, that's all I want to kind of talk about in terms of pendulum. That means, we are going to be looking at period and, equations for oscillations, right? But or more or less, it's going to be pretty much that. So that means you have the theta as a function of time that is equals to, let's say, theta max, then cosine omega t plus phi, right? That's the equation, right, of the motion. And then you can say, like, let's say omega, which is, angular frequency, right? So we don't really, go beyond that. So mostly in terms of, if anything, we're going to be, maybe seeing something like this on the homework or recitation. But other than that, mostly for the pendulum is in terms of its frequency and period. All right, so let's look at one example and we can then complete this chapter. So this example is actually shows how we can use the pendulum and what the Galileo did, right, to understand that when the pendulum is oscillating, only thing is basically the length of the string is important. So it is said that Galileo discovered the basic principle of the pendulum, that the period is independent of the amplitude. by using his pulse to time the period of swinging lamps in the cathedral as they swayed in the breeze. Suppose that one oscillation of a swinging lamp takes 5.5 seconds. How long is the lamp or the lamp chain? That means, you want to find the length basically when you're given, the time for one swing, which is basically the period. Taking period equals to 5.5 seconds. And then we know that the period is equals to 2 pi square root of L over G. Then what I can do here is first, you know, square everything, which gives you then T square equals 4 pi square, then L over G, and then rearrange this and solve for L, which is equals to G times T square over 4 pi square. All right, so then we pretty much plug in everything, right? 9.8 times 5.5 squared and divided by 4 times pi square. And then the lamp length is then 7.5 meters. Right, so this is then part A. Part B then says this. What maximum speed does the lamp have if its maximum angle from vertical is 3? Well, this 3 is 3 degrees. So, I mean, it's 3 degrees. That means think like this. So taking the pendulum, right, where this is its equilibrium, and move it to 3 degrees, like that. So, and then let's say you let go. When you let go, then it says it's going down. We want to know, let's say on its way down, right, how fast it's moving when it reaches this bottom, right? What's maximum speed? Because maximum speed, remember, again, happens when it is at equilibrium, because this is basically, in a way, x equals plus a. So it's going to go oscillate between x equals plus a and minus a. And the maximum speed happens at the equilibrium position again. All right, so now how do we solve for that? Well, we can solve this by using the energy approach, because remember, what makes it go back and forth? Gravity. And what type of force is gravity? Conservative force, which means I can just look at it in terms of going from point A to point B, where point A has some height above, right? And then go to B, which B is my equilibrium. That means in a way I go like this. So this is my point A. So this is length L and this is length L, right? So that means it's, going from point A to point B by covering basically this distance. I'm going to take B to be my equilibrium position, Y of B equals 0. Then I have Y of A. Now, I have then kinetic energy at A plus potential energy at A equals kinetic at B plus potential at B. Now, because it starts from rest, there is no kinetic at A. Reaches B, there is no potential at B. Which means then all I have here is potential at A equals then kinetic at B. Okay, then I have 1/2. Well, let's do this. Well, in a way, right? The other way around too. So 1/2 mvb squared, then it equals to then mgh or mgya. I can still cancel the mass and then solve for vb, which is then square root of 2gya. The question is then, how do we find this A, position of A? Well, one thing I have here is this. We calculated the length, 7.5 meters, and then I know it goes 3 degrees. That means the height of A is just this distance here, which is, think like this. This is where we use, a little bit of, geometry. So this is L, and this is L cosine of theta. That means Y of A is L minus L cosine theta, or L times 1 minus cosine of theta. That means then VB is equals to square root of 2 times 9.8, then times 7.5 for L, then 1 minus cosine of 3 degrees. Plug in everything, and I get VB as 0.45 meters per second. And that's my final speed. Again, using this, trigonometry, where I need, again, I need to find this length, right, which is this is L, and when it's moved here, right, when you move the pendulum here, this distance represents the L cosine theta, its projection. So then the difference gives me my height of the position A. All right. So that's then concludes this chapter.